Thank you guys for sticking around. This is sort of probably a long story. I'll try and make it into a short story about why we're having this event. But we have a focal point grant on campus that was given for this topic: interdisciplinary research, development in algal biomass, biofuels, and bioproducts. So that was awarded in the fall, and Yen Zhao, who's in the back there with the video camera, was actually the primary force behind going ahead and organizing this grant application. And basically what we're trying to do is just build the networks on campus between the students, between the faculty that are interested in this topic, algal biomass, biofuels, and bioproducts. And we've got some money to go ahead and bring in some speakers and hold some other events to try and help foster those connections. And so hopefully we can be in a better place to pursue opportunities that come up in that particular area. And so if you're interested in those topics, there will be more events. This one was sort of done at the last minute, and we probably could have been a little bit better organized, but we decided to take advantage of Dr. Turner coming up to campus here and do a little something on the topic of hypoxia. But if you're interested, if you have some other ideas for speakers that would be good to bring in, you can tell me, you can tell Yen. We've got a Google Doc going with just sort of open discussion on the general topic. And so we would be glad to, the whole idea is to start building those connections, and so we hope to be able to make this the first step in that process. Okay. But today I wanted to talk a little bit about building on the problem of hypoxia. What are some things that we can do for it that would potentially have some of the near-term impacts? We talked about the problem as being something that will take a long, long time to solve, and we're fully in favor of those long-term solutions. But in the meantime, is there something that we can do that could potentially provide a benefit in the short term and/or reduce the costs of providing that mitigation? And so Juping Ko is actually the one who should be giving this talk. This was his master's degree work, but as I said, we sort of decided quickly, and he wasn't in the room when we decided to put this seminar together, and I didn't want to force him into doing it, so I said I'd just go ahead and do it myself. But if we have any tough questions, then Juping's going to actually have to be the one that answers it. So in any case, that's the general topic. Go ahead and go on here. Okay, so we don't really have to do too much. How many people were not here for the last seminar? So just a couple. I know you guys are aware of the problem of hypoxia, but basically it's a condition of low oxygen concentrations, and there's a zone that is created in the Gulf of Mexico that varies in size each year. Here's the size range that we had from some historical measurements. Sounds like it's actually gone up now a bit here recently, and then the EPA goal is to bring that down to 5,000 kilometers. Okay, we talked previous talk, we talked a little bit about some of the impacts, so we won't spend too much time on that. If there's anything here that's new. We didn't talk much about tourism. What's your opinion? Does it have an impact on tourism, or is that sort of, I mean, we read about that, but since we don't live in the area, I guess I'm curious if that's actually a real impact.
Not too much, I would say, because the fishermen are coming down, but the sports fishermen are not usually coming down to the hot weather in this June, July, but they are there in February and
Okay.
other times.
Okay. We talked a little bit about the mitigation plan, but I think it's worth quantifying a couple of things here. So the original EPA advisory board recommendation was a 40 to 45% reduction in riverine nitrogen, and it sounds like now those projections would have to go up, upwards of 60% if they actually wanted to solve the problem. And then the other major proposal that I've run into is to convert the riparian farmlands into wetlands. I've done a little bit of work on engineered wetlands for my master's degree. I know they're not cheap, so I'm not surprised to see a cost here that's been estimated at about $5 billion to put in enough wetlands to significantly address that problem. And in either of these situations, I think it's worth noting that the lag time for the beneficial effects is still there. that if you go ahead and do this, it does put in motion a situation where you can resolve the problem in the long term, but there is still a need to potentially solve that problem even faster.
Just to be clear, the advisory board called for a 45% reduction, but not through reduced fertilizer use. They called for it through a whole range of practices, and reduced fertilizer use would just be one practice. It was not.
Okay.
It was not nearly that specific.
Did they specify for fertilizer specifically how much there would have to be, or is that
No.
what their part of the reduction was? Okay.
No, it was just I was part of that, so
Okay.
it was a big table of all the practices, and so it was clear that there's no one practice that will do it. So it's a whole range of, and the practices vary whether it's tile drain, subsurface flow, surface runoff, and nitrogen or phosphorus. So it's a whole range of practices that would be called for to meet the 45% reduction goals.
And I'd say, I mean, I come from the wastewater world, and so one of the places that gets clamped down on is to go to the wastewater plant and say, we need to keep cutting down the nutrient loads that come out of the wastewater plant.
And that was called for as well.
Right. In that particular case, I'm familiar with the costs of that, and it's about, well, it's anywhere from $5,000 to $50,000 per ton. That if you want the wastewater plant to take it out with their facilities, it's a relatively high cost to get those, get the nitrogen out of the wastewater plant. My suspicion is, although I haven't done any work in that area, is that taking it out of the farm land would be a much more cost-effective way to do it. And there are a few situations where wastewater plants have actually gone to local farmers, and instead of meeting their own nitrogen and phosphorus goal, they've implemented some sort of best management practice on the farm, and we're able to meet the target for the stream without having to actually put in the engineered facilities of the wastewater plant. So the objectives for this particular work were to look at a new concept for mitigating hypoxia, and that's specifically to go ahead and harvest the biomass and then turn it into a biofuel. In order to do that, we needed to develop a techno-economic energetic model to basically compare the harvesting energy inputs and the fuel that you could go ahead and harvest off of that algae. And then potentially try and look for good topics for further research. So identify what are some of the important issues that came up in that evaluation, and say what can we do to try and improve on what's currently available. Okay, so Co came up with the name for the model, harvested algal biomass for energy recovery. And at first I thought that's a very strange, but then because we're dealing with a nitrogen problem, I think it is a very apropos title for the model, because we have Mr. Haber to thank in large part for the nitrogen that we have available in the Gulf of Mexico. Okay, so this was the idea of the model, was break it into a couple of different steps. There's an algal production step, which is happening in the natural environment. We've got a harvesting step, and we looked at, in this case, 4 different harvesting methods. Actually, Co looked at more harvesting methods, but just to try and keep it simple for today, we'll talk about 4. And then in the conversion area, we looked at 4 different types of attempts to turn that algal biomass into biofuels. First one is hydrothermal liquefaction. So that's a pressure cooking kind of process, probably what the Earth went through to make our petroleum reserves in the first place. And that produces a crude oil product. It would have to be refined if you wanted to make it into a transportation fuel, but it can be burned for heat and power if you wanted to do that. Anaerobic digestion, which yields a methane product. And then we had 2 sort of higher level fuels, so a biodiesel through transesterification and ethanol through fermentation. And in both of those cases, there's some fairly important pre-treatment steps that would have to go on with the biomass, so you can't take the original biomass. And you'll find out a little bit later, but there's a pretty strong line here between what makes sense, which is above the line, and what doesn't make sense for naturally harvested algae, which is below the line. So in terms of the algal biomass quantification, we used satellite imagery to go ahead and calculate how much biomass there could be available, where it's located, and basically the satellite imagery looks at the reflected sunlight, and because the algae that are operating tend to reflect the green light, you can correlate the strength of that signal to the amount of chlorophyll, which is measured routinely and come up with a correlation. So it's perhaps not exact because different algal species have different amounts of chlorophyll, but there's a lot of good information on that, and we know when those species are likely to be more or less dominant. So we can go ahead and go through a calculation process to estimate the amount of algae that's available in some depth. And the sampling depth is variable depending on how strong the bloom is. So the stronger the bloom, the more we're sampling in just the top waters, and then if the bloom is not quite so strong, then we're probing a deeper amount of water to get the signal. These are some examples of the processed images whereby we would go in and try and identify the areas that are most highly occupied by algae. So if you go ahead and use that satellite imagery, and then you can go ahead and make an estimation of biomass in what we call the highly eutrophic area. So the highly eutrophic area, is it 10 milligrams per liter? This was the cutoff in this particular case? Okay. So we looked at different cutoffs, but in this particular case, the cutoff was chlorophyll A above 10 milligrams per meter cubed. And then if you look at over time, there are of course variations in the amount of biomass and the amount of area that falls into this highly eutrophic cutoff category. Okay, so on the harvesting technologies, mentions there were 4 that we're going to talk about today: plankton net trawling, a traveling screen, which is what's used in some commercial applications where they go out and harvest naturally occurring algal blooms and use them for nutraceutical products, with and without a focusing arm to sort of bring the algae into the traveling screen, and then a screw pump filtration method that also used a focusing arm to get a wider collection area. So these are some pictures to give you an idea of the types of technologies that are available, the plankton nets. This is a artist rendering of I think this one's not a real photo here, right? We've got a real photo a little bit later, but this one I think is just a sort of a picture of what that would look like. A screw pump is over here, and the idea of a focusing arm to sort of try and guide the algae into a collection point like this or like that. Ah, there's the actual picture of a real one. So these are actually used in some cases for collecting, like I said, relatively high value algae that's then put into nutraceutical products. Okay, so this gives you a picture of one of the important energy consumption analysis that was done. So on the left-hand side here, the first graph, we have energy consumption, gigajoules per kilometer squared versus depth. Depends, obviously, the amount of energy you spend depends on how far you go down and try and collect the algae from, and the 4 different methods. And in this graph, it's good to be low. And so in this particular case, it shows that the plankton net trawling had a lower energy input per kilometer that you were going to go and harvest. Okay? This one is sort of the reverse situation. It's harvest efficiency. It's the tons of biomass that you would bring in per gigajoule that you would spend. And in that case, the plankton net trawling comes out the best. So here it's good to be on the high end of things. And of course, again, it depends on the depth that you're harvesting. The most efficient harvest is at the shallow depths, and then it gets a little bit less efficient because you're generally going to pull less algae per amount of water that you're processing. Okay, and looking at the conversion model alternatives, you mentioned there were 4. All of them go through an initial dewatering step to go from something like 1% dry weight up into the range of about 20% dry weight. All of these methods will work much better in terms of an energetic balance if they're running at least 20% dry weight. But then a couple of them, in particular the biodiesel, the conventional extraction methods require drying the algae, and so there's an additional drying step here to get up into the 85–90% dry weight category. Okay, and that turns out to be very bad for an energy balance situation. And in fact, we just got back from a algal biomass conference last week, and pretty much people have given up on dry extraction. If it's not going to be wet, you're never going to have a positive energy balance, is basically what it comes down to. These other methods, hydrothermal liquefaction, anaerobic digestion, can do a pretty good job with wet biomass. And so you don't have to dry the biomass out in order to get the energy out, and that turns out to be a good thing for trying to make a positive energy balance. Okay, so again, this just pictorially sort of shows what we're after. I would like to highlight this one because most people are less familiar with the hydrothermal liquefaction. But that's an example of the actual oil that you can get out of that process. And again, this is a crude oil. You can use it for burning, but if you wanted to actually make transportation fuels, it would have to be cracked and refined just like you do with conventional crude. Okay, this graph has a lot of colorful lines on it, and all these lines essentially are related to different species of algae that are known to exist and for which there was some data on their chemical makeup. And then basically if you look at the chemical makeup, you can determine which type of conversion method would be most suited. So some of these algae are high oil algae, some of these algae are high carbohydrate algae, and so depending on what their particular situation is, they might be better for transesterification, for fermentation, for anaerobic digestion, or for hydrothermal liquefaction. But the main message here is that this is sort of the zero line. This is a, you're putting in as much energy as you get out, and for fermentation and transesterification, everything is below that because of those pretreatment steps. But for anaerobic digestion and hydrothermal liquefaction, you can generally stay above that level as long as you were harvesting in an area where the chlorophyll was, say, somewhere above 10 milligrams per meter cube. This gives you an example of just of what the model input pages look like. And so it's done in Excel. It's nothing terribly complicated, but you can go ahead and go in there and you can pick all sorts of different parameters, change the parameters, and then see what the output is in terms of the energy balance or other parameters that you're interested in looking at. Okay. This is a base case analysis where we looked at just going ahead and going out and directly harvesting with the method of the plankton net, because that turned out to be the most energetically favorable harvesting method, and then looking at two conversion methods, the hydrothermal liquefaction and the anaerobic digestion. And you can see that in both of those cases, so in both those cases you had to be north of 50 milligrams per meter cubed of chlorophyll in order to make a break-even energy balance, okay? So we looked at that and we said there isn't too much of the Gulf that's in that situation, so that wouldn't be a advantageous scenario. And so we looked at ways that we could try and push those lines back and get to a positive energy balance without having to have such a high chlorophyll concentration. Okay, so one of the ways to do that, well, I guess I should highlight on that last graph, is that the majority of the energy was still for driving the ship. Okay, so that's one of the take-home messages is that if you want to try and improve your energy balance, one of the ways is to try and do it without having to drive a ship all over the place to collect the algae. On that, I guess, theme, one of the ideas is to try and hook up to a stationary cultivation harvesting arrangement. This is one that NASA has put forward for essentially a plastic dialysis kind of membrane that would actually just sit there and go ahead and accumulate the algae, and then you could come and collect the algae from that location. There are also a lot of oil rigs in the Gulf of Mexico. Some are inhabited, some are not inhabited. But these would also provide potential sites where you could do algal harvesting in a stationary manner. There's one company I'm aware of called Live Fuels, and they're proposing to pump some of the nutrients up from the low sediments in these locations, let algae grow, and then actually their interest is then to grow fish on the algae, and so they go ahead and use the fish as sort of the collection or harvesting method. At least that's what they're proposing. And you can see in this case, you're able to drive it down to where, with hardly any chlorophyll in the water, you can have a positive energy balance because you've saved all the energy associated with driving the ship around. Okay, but if you still did want to drive the ship around, the best alternative that we came up with is to go ahead and float the algae to the top, and then go ahead and skim off just the top layer. So in that situation, hopefully the animation works here. It would be something like this. You'd have a boat going through the water, it's bubbling in air, the algae gets floated up to the top, and then you collect it in your plankton net that you're dragging behind the boat. Okay? So in that situation, we found that you could drive the chlorophyll balance all the way down to around 10 milligrams per meter cubed of chlorophyll, and as we mentioned earlier, that was one of the screens that we used for determining the highly eutrophic areas. Okay? Is to get to about 10 milligrams. And there is a significant amount of area that's above 10 milligrams per meter cubed at different times of the year. Okay? We did some lab testing. Co actually went down and sampled some algae from the Gulf of Mexico and then brought it back and grew it up in the lab. And in those situations, we were able to get about 72% of the total biomass collected at the surface. For the models, we assumed 50% collection efficiency, but it could actually be higher than that. Okay, so what does this come out to in terms of an overall energy balance? You can see here the eutrophic area that was determined to be above 10 milligrams per meter cubed. You have total biomass, the amount harvested, how much energy you spent on the ship driving around, the biofuel energy that you could produce from that. So in the case with flotation, you can see that that energy value is greater than the harvest energy, but in the case without that, it's actually below that. So we have a negative energy balance without the flotation, and then that is expressed here in terms of the equivalent fuel in terms of a barrel, and then the value of this at full market price for crude oil. And so this is intended for the peak month in April. Okay, so there would be about $1 million worth of oil that could be harvested from these highly eutrophic areas in that situation. Okay. The other thing that we're very interested in, of course, is the environmental impacts of doing this. Okay, we realize that there's going to be some things that are good and some things that are bad. And this particular slide is looking at one of the things which would be good is that you remove excess biomass from that would eventually go through some sort of aerobic respiration, and it contributes to the depressed oxygen in the water column. And so really all I think that I want to highlight here is that in this net positive energy case, the actual impact on the lowest 1 meter of the water column would be to increase the dissolved oxygen concentrations by about 2.8 milligrams per liter. Okay, so it's enough, potentially enough, to get it above the hypoxia criteria. In the case with the net harvesting, where you weren't removing as much biomass, you only have a half a milligram per liter effect spread out across that bottom layer. Okay, so the main conclusions here are that plankton net trawling was the most energy efficient way that we evaluated. Anaerobic digestion and the hydrothermal liquefaction were both viable methods for converting that energy, or converting that biomass into an energy product. With flotation, we should be able to operate at a positive energy balance anytime that we're above 10 milligrams per meter cubed. And then finally, that if you did go ahead and implement this, you could, in the best month of the year, you could produce about this many gallons of crude oil if you use the flotation as a vertical focusing technique. Okay, so the main part there. And then, of course, we said that we're interested in future work, and the whole idea of the focal point is to think about what comes down the road. Some areas that we've identified, I'm sure there's many others, but some areas that we've identified interest in is doing some of the environmental impact modeling. I'm sure at LSU there's people that are devoted to looking at the environmental impacts, and so could we do some modeling where we say, okay, we drive this boat and we clear this alley of this much algae, what are the impacts on hypoxia if you do that? What are the impacts on the fish fry? We mentioned that could be a negative impact. So all of these kind of things we feel like obviously have to be looked at, and we're very interested in trying to look at what those effects are. Of course, you could apply the model to other locations. This particular picture is from Qingdao. showing a rather extreme macroalgae bloom that occurred there before the Olympics. I think Dr. John could tell us about the heroic military effort to try and move that algae out because it was the site of some of the water sport activities for the Olympics. Okay. We think there's also the potential for some valuable products in certain algae products, so EPA, the omega-3 fatty acids. So if we're going to harvest it for the fuel, we could take the biomass, and if there is high-value products in it, first extract those high-value products, then use the leftover biomass for energy. Okay? And then, in terms of new technologies, we think there could be some work on the actual focusing technologies that you would use to harvest the algae. We think there's a lot of room for an intelligent system for determining where you would actually go to harvest. Okay, so the weather patterns, the currents, all this kind of information is pushing the algae around. You could have a real-time intelligent harvesting system that's sort of predicting what's the best path to drive the load if you wanted to go ahead and do that. And then, of course, stationary algae farming we highlighted as being a potentially advantageous topic to take a look at. So I think with that, we've got some acknowledgments here. Dr. Zhang, who we worked with very closely on the liquefaction aspects. This work was actually supported by the College Office of Research, a small grant, but it was enough to support Chuting to do this work, and so we want to give the thanks there. Chuting was able to get on one of the LumCon ships to go down there and do one of the hypoxia cruises, and so we're thankful for that opportunity. And then with respect to the satellite imagery, we've also had some assistance in that area. Okay, so that's it. I guess one thing I'd like to point out is that we do have a website that was built as a part of a student sustainability project that we did on campus, and now we've maintained it for other things algae related, and it's just called algae.illinois.edu. And if you're interested in seeing some of the other projects that we've done on campus or that we're interested in pursuing, then that's a good place to go, and then you've got everything else to do. So with that, I'll go ahead and entertain some questions.
Maybe I missed something, but the scale of some of this is interesting to me. Is it 28,000 tons is the estimate of algae, or was that the harvested algae? Can you back that one? Of the harvested or the total? That's, in the scale of biomass, trivial, right? Don't we get that on a few hectares of corn? Right?
You might get 20 tons on it. I mean,
Well, you got, that's tons, that's not even carbon, right? That's just tons. Yeah. But, if you, all right, 10 acres of corn, right? So it seems to me that there's two issues here. One is the harvest. It's a tiny amount of biomass in the scale of things. So why even worry about doing something with it? I mean, if this truly could be done for, I don't know, a couple $1 million, maybe is that the end of it?
Go ahead and do it.
Well, who cares about the other side? That's true. I mean, that's not enough biomass to worry about.
So 15,000 tons right here?
That's nothing.
So you need, I mean, I guess I'm not a corn guy, but isn't corn about 5 tons an acre? In terms of total biomass?
Well, more 10. But that's still not that much. I mean, or thousands of, it's still not that much biomass.
Well, I mean, I certainly would think that once you've harvested it, if you're right, you have to ask the question: is it worthwhile to spend the money to go ahead and do a conversion process? Personally, I think it will be, but if it's not, then I think you're right that you could just go ahead and try and harvest the biomass off. But as an environmental engineer, I'm always looking for trying to make things as carbon neutral as possible. So if I'm going to spend fuel to go harvest the biomass, if I have a choice, I'm going to try and offset that fuel with some renewable product. And so in this case, we could just bring the algae out, throw it on the land. That's what the Army did in Qingdao's case. It just took it up into the highlands and dumped it on the ground. So that is possible, but I think it would be, from an environmental perspective, we could actually have a positive impact as opposed to just having a neutral impact. But I do think it is important in this case that I think that energy balance may not be enough, and the cost, the $1 million worth of fuel may not be enough to justify doing it on an economic basis. But I think what we have to do is compare it to the other options that we have for accessing the environmental benefits. So if we're going to do something like go put in additional wetland area, that's not a zero cost option. That's a significant cost.
Right, well, I was just saying, putting in bioreactors, yeah, I was off by, it's more like 1,500 acres.
Yeah.
of
Right.
land. Or that, but that's still, in the scale of things, absolutely tiny. I mean, you talk about biomass, but if we could go harvest the algae for $1 million, that's a lot, doesn't come anywhere close to the billions we're talking about.
Right.
For,
I'm definitely in agreement that the scale of, the order of magnitude of these numbers is measured in millions, and the order of magnitude that we're talking on the other things, for wetlands anyways, is in the billions. Now, reducing the fertilizer, I mean, if you don't need that fertilizer, is a good thing to do, because that's a savings all across the board, and it should just increase the overall efficiency of our agricultural operations. If it's a situation where we're putting on nitrogen and that's serving as crop insurance, it's, the
well,
reason farmers are doing
we
it.
don't really think that's true for the most part,
Okay.
so I don't think it's over application, but it's just that, I was just struck by that there is not that much, and is that really, that seems like a really small number of biomass. Does that seem reasonable?
Right.
I mean, is
That
that,
seems small, but I don't know. I think you don't have to hitch it to hypoxia at all. It's just, if you get a yield for that much, you get that much. I wonder if, well, I can give you a link to you're collecting it out of a flat surface, but the Gulf is anything but flat. It's got storms. You won't get 30 days in April for anything.
Okay.
And it's being stirred up, so I wonder about the, I mean, I could give you a wave site, you can figure it out yourself. But there's, look, we have wave values and turbulence values, morning out there, so you can maybe see how many days you can get it under the conditions you got in the lab. Decide if the bubbler is really useful, or how many days,
Initially, you based on 10 milligrams per cubic meter. That's for algae density.
That was the.
Would that be a typical, or you just hitting the low end?
So if you, in this particular case, in the April, if you cut it off at 10, this is the number of kilometers that would fall into that category. So if the total hypoxic zone a few months later, in 2010, I think this data is from, was 20,000. So this was approximately, 1/6 of the total area of the hypoxic zone. Falls into that category. Yeah.
I didn't catch it, but did you do an estimate of just how much nitrogen you'd be removing from that area?
That would be the key measurement. There's something about the eutrophic areas. But if you figured out how much nitrogen, well, you could figure out if that's, you're saying you're going to remove 10% of the nitrogen?
Well, I mean, in this particular case, the nitrogen is probably between 10 and 15% of the biomass concentration. So if you,
So 10%, you could remove 1,500 tons?
right.
I mean, that could be a significant removal, that could, if you're getting
that's 1.5 million tons going down the river.
right at high times, but sometimes it's lower, too, isn't it? Between 0.9 and 1.5.
There's more, 10% of the nitrogen is going to be important. In terms of the impact on hypoxic zone, it's the percentage of the nitrogen you're going to remove. So, and that's, you say it's 1.3?
No.
Per year or per month?
1.9 and 1.5 million tons
Per year.
per year.
So this is 1 month.
So let's say 100,000.
So
That'd be 10,000. Anyhow, the thing is not the effect on the hypoxic zone, or whether it's economical regardless, and there's other factors.
So by removing the algal biomass, you're just saying another set of algae would grow.
Yeah, if you don't remove
Yeah.
nitrogen, it's going to grow something else to replace it.
But take the biomass out, obviously.
Right.
But then you're taking out the nitrogen. And so you don't remove the eutrophic area permanently. It's right behind it, it's filled up with corn.
Right.
The river's flowing through it. It's just replaced immediately.
But does it take some time for the algae to grow back? A day? Okay. That's why we like it for biofuels.
Lance, how deep were your bubblers?
We assumed that we would bubble down to 5 meters. Yeah. And so we would be trying to harvest a significant fraction of whatever's in the top 5 meters. And so yeah, the question on the waves, does that have more of an effect on the netting operation? Or would it have?
The bubbler, I think, would be interfered with. The effect of the bubbler would be compromised by waves.
Yeah.
Just because they don't care.
Right.
Because presumably they come out from the bubbler because of turbulence. And if there's background turbulence already, it's just going to redistribute.
Well, you're just trying to change the density of the algae just a little. I mean, they're close to the density of water, so if you just attach a few air bubbles to the outside of biomass, then it's a very common technique that we use in wastewater treatment is to pump in a little bit of dissolved air, and you can float everything up to the top. So I think it'll still float, but once it gets to the top, it may be easier to re-liberate those bubbles, and then some of it will go back down.
According to Wikipedia, 2 to 6% nitrogen in
Well, I'm just going on the, this kind of general biomass formula. That's about, I think that's about 12% nitrogen for algae.
Yeah.
We've got 2 to 6% for
Plants, including algae, can preferentially accumulate carbon, and they're quite flexible in their C/N ratios. So, you need to take that into account.
Okay. This is what we do for bacteria.
Bacteria have
Yeah.
10 times the amount of nitrogen phosphorus as algal cells because of that capability of algal cells to accumulate carbon out of balance to the rest of their carbon.
I always assumed that algae would actually be better because they don't need to grow heterotrophically. So they can just, their limiting nutrient is the nitrogen. So okay, well, 2 to 6%, so lower that down by a factor of 2 to 5, what we were talking about.
And that'd be like 0.1% of total, total land going in, I guess if you do it in 1 month. So 1,580 tons divided by 1,500,000. 500,000.
So I guess I would say though that you could turn right around and keep harvesting. The issue is can you get something beneficial out of the harvest? The harvesting is only limited by either the economics or the number of ships that you've outfitted to do that job.
Is there anybody out there actually doing this yet?
No, not that I know. And that's why we did the energy balance, was to show whether or not it made sense to try and do it.
But I guess I'm just saying, for the scale of that, I mean, if we're, hypoxia is a problem we think we can solve this way, the amount of money is in the scale of doing something for agriculture is pretty trivial compared to sewage treatment plants and, as you said, in agriculture, and the amount of energy is, 1,000 acres of corn. So it's a tiny part of Champaign County. So, why worry about that part? It's just, I guess if it's to solve hypoxia, it's one thing if you're trying to make the main goal is energy, but if the goal is really hypoxia, then the effort is all just having to scoop up all the algae, which I still think is pretty hard.
Well, I'm sure you are. Concern first is can you make it economical regardless if that has any effect on hypoxia?
Well, no, I think of it I don't think we would have thought of this apart from trying to solve the hypoxia problem. Because if we want to just grow algae, I'll go to the wastewater plant. I can grow a lot of algae at the wastewater plant. And that potentially has the same long-term effect in the sense that we're keeping that nitrogen from going down the river. But But the only reason we thought about this is when we looked at the scale of, and the cost of the wetlands, which was the only costed alternative that was out there. I knew that we could do it for less than billions. In that particular case. Right? I had the intuition that we could do it for less than billions.
And if you could remove the nitrogen and still make a profit on it, I mean, that's the thing that is very difficult to do on land. If we can remove the nitrogen, we can design these systems, but they're very expensive. If you could do that and plus make a profit,
Or break even,
or even break
offset your
even,
costs.
that would be tremendous.
If you're removing biomass, you can keep them, right?
Yeah, I mean, there are social costs too. I mean, in that, I can just see you trying to talk to the Cajuns about, you take in their fish larvae and.
Right,
There's
there's
an
the
entirely
ecological
different
side.
set,
Yeah.
Right.
because the fisheries, being threatened
Well,
by,
and
like any power plant, loses, through the thermal cooling apparatus, they have their permits, mainly because they are taking larvae into the screens, smashing them, and then you have to compensate for that. And it's a large, just as a note, there's more water through cooling plants than there is water through south of St. Francisville, which is in Louisiana, than there is water coming down.
Wow.
I mean, they really filter the heck out of it.
Who does this?
All the industry,
What, for what?
for cooling,
For pulling what?
nuclear power plants, industry,
Oh, in Louisiana?
and the Mississippi River.
Huh.
You think they use more than the actual?
There, more water's flowing through them than goes by them.
Wow.
Yeah, that's right, that's an industrial, it freaks up on them, right?
So the fishing, I mean, this was April, so
And that's the
presumably
worst time, because that's when the menhaden larvae come in.
Okay, so,
And rush.
so if you, is there a time at which you wouldn't be fishing those areas because they're hypoxic? Or do you continue fishing those areas even after they go hypoxic?
the hypoxia happens after the algal, right?
Right, but we can do the
Yeah.
same thing with the bacteria as well. I mean, the bacteria, you would lose some
You're
carbon.
gonna use a 1 microplankton net?
You don't, I mean, I do a lot of filtrations for bacteria where we use sand. And sand is, I mean, the filtration doesn't require 1 micron to get the bacteria out. I mean, yeah, the size of the pore is only a small factor, because actually what happens is you build up a layer on top of the filter, and then you can filter almost anything out.
So, you know, Dean was talking about the social implications of showing the big plankton around the Gulf of Mexico. I think there's also environmental implications of pitting yourself against, as an alternative to wetland restoration. Wetland restoration has more positive environmental
Sure.
ecological benefits than just
And I share,
removal. There's habitat and floodwater retention and sedimentation and stuff like that. There's all kinds of ecological benefits. So I don't think that I don't know that that's a good direction for you to go. I understand that you were coming up with a cost-effective argument, but I think.
well, I would say do both.
No, I agree, yeah.
My master's degree, I did engineered wetlands. I'm fully in support
Yeah.
of wetlands. I think that we should do that, and that's a better long-term solution.
Right.
The issue is we haven't been able to muster the resources to do that, and even when we do muster those resources, if we do, it's going to take a long time for that to kick in. And so I would say this is a temporary effort. You can see the kind of things that we were talking about are not big, custom modified ships. You know, we didn't go out there and say we're going to design the perfect algal harvesting vessel. We said let's do something that can be temporarily added on to an existing vessel and not cause a reworking of infrastructure and that sort of thing. I mean, there's a lot of ships that run on bunker oil, which is, the low end of crude. I mean, you could actually probably just have the ship go out and constantly supply itself with fuel.